Welcome. In this lecture in linear data analysis, we'll explore ways that we can improve the perceptron model of an artificial neuron. The main concepts for this lecture are that linear activation, which is what we've been exploring so far, has a limited ability to separate data vectors. But the semi-linear was one term for an early use of a logistic function, so that brings probability and logistic functions into the world of artificial neurons. To model the errors, we can use least squares, and we can also explore probabilities. We'll concentrate on least squares methods. And all of these are really bridges to other areas of machine learning. That is, we'll be learning a linear separation using a hyperplane, but we'll be using nonlinear methods to do this. And these nonlinear methods are widely used in statistical reasoning and in artificial neural networks. One problem that we can think of as we go through this lecture is how can we learn the best separation, indeed the best hyperplane separation of data that we're given. So in the perceptron world, there were known difficulties. The original perceptron was proposed in 1958, and learning the threshold was proposed in 1960. So Minsky and Papert in 1969, Marvin Minsky was the founder of the MIT Artificial Intelligence Lab, and they pointed out that they were able to prove that a single perceptron or a layer of single perceptrons can't learn certain types of problems. And they called these exclusive OR patterns as one of the most prominent patterns that were very simple to describe, but you couldn't learn using a single or just a couple of perceptrons. So their criticism was aimed at one-layer networks. They recognized that multi-layer networks were possible, but at that time, people didn't know how to train or learn with a multi-layer neural network. So the impediment was basically that the activation function was binary. In the end, this is what researchers resolved. The classic data that we have are non-linearly separable, and we can think of these as forming in a truth table an exclusive OR. For example, if the rows were the labels of the data and the columns were the classification, if we had this sort of pattern, we wouldn't be able to distinguish it. So here, what we have are our positive set is in this group and in this group, and our negative set is this group combined with this group. And there's no way in two dimensions that we can separate these data. So this was an example of a problem that was recognized early on in artificial intelligence as being difficult to solve with a perceptron. Error propagation was proposed as one way to learn multi-layer neural networks. It was proposed first in 1985 by a famous paper headed by Rumelhart, and they devised a way to propagate the labels through a multi-layer neural network. They suggested using the logistic activation function. Their 1986 paper in Nature is most widely recognized, and the corresponding author was the Turing Award winner Geoff Hinton. And this is widely cited as foundational in reviving interest in neural networks. And it was really a rediscovery of work by Paul Verbosch, who did it in 1974 in a very hard-to-find PhD thesis out of Harvard. So in this lecture, what we'll do is we'll only consider a single neuron, and what we'll do is we'll use this logistic activation function and explore what we can do with it.